Dear colleagues, I would like to present a result of our research investigation of PNN optimization methods to improve classification performance in transplantation medicine for the sixth International Conference on Informatics and Data-Driven Medicine. This paper was prepared by Miroslav Havryliuk, Nazarij Hovdish, Yaroslav Tolstyak, Valentina Chupyak, and Natalia Kustra. Let me introduce myself. I am Miroslav Havryliuk, PhD student at the Department of Artificial Intelligence of Lviv Polytechnic National University, Ukraine. I obtained my bachelor degree in computer science in 2020 and my master's degree in computer science in 2021. Let me talk about our research. The problem of predicting the success of organ transplantation is critical in the field of medicine. Currently, there are no models capable of accurately describing the patient's condition after transplantation. Therefore, the use of methods of intelligent data analysis has gained wide popularity. However, insufficient data is often an obstacle to building adequate machine learning models. Classical models of artificial intelligence do not demonstrate sufficient efficiency in the case of processing small medical datasets. This is due to a number of reasons, the main of which is the problem of overfitting. The use of a probabilistic neural network in such cases can improve performance compared to traditional models. However, the selection of the optimal network parameter by brute force methods requires a lot of time and computing resources. That is why the use of optimization methods is appropriate for this task. A probabilistic neural network is often used to solve a wide range of tasks, including classification. The training procedure of this neural network is quite simple. The model also has certain disadvantages, the main one of which is the increase in dimensionality of the structure with the increase of the sample. Accordingly, the use of probabilistic neural network can require the allocation of a large amount of resources. PNN has only one parameter, sigma. The work of this neural network in the case of binary classification can be described as follows. Let there be k vectors of class 1 and m vectors of class 2 in the sample. The task of the model is to classify the input vector. Therefore, it is necessary to determine the probability that the input vector belongs to class 1. The first step is the calculation of Canberra distances between the input vector and all vectors in the sample. In the next step, Gaussian distances are calculated based on the obtained values. Then, the probability that the input vector belongs to class 1 is calculated by the formula 3, and similarly for class 2 using formula 4. So probabilistic neural network predicts a class of the input vector using these probabilities. For models that are built using unbalanced data sets, the F1 score is an appropriate measure of performance. So in this optimization problem, F1 score is the objective function. According to the real and predicted values of the target attribute in the test set, precision and recall can be computed using Formula 6 and 7. And according to the definition of the F1 score metric, it can be expressed as in Formula 8. Thus, the problem of F1 score maximizing can be presented in the form that you can see on the slide. We applied three popular optimization algorithms: Bayesian optimization, differential evolution, and dual annealing. These methods do not require the calculation of derivatives and can perform optimization in the case the objective function is a black box. You can see on the slide the k parameters of every optimization algorithm we use. We used a dataset that contains outpatient case histories of 152 patients who received HLA-compatible renal allografts in the Lviv Regional Clinical Hospital. The target attribute is the success of transplantation. So, as you can see, it is a binary classification problem and data is small and imbalanced. We separated the dataset randomly. 80% for train set and 20% for test set. First, we applied a grid search on the interval 0.00001 to 10 with a step 0.001. The execution time was approximately 42 seconds, and the number of objective function calculation was 10,000. As a result of the experiment, it was found that there are two intervals on which F1 score reaches a maximum of 0.842. Then three optimization algorithms described above were used to optimize the parameter. The implementation of optimizers from the SciPy Optimize and Bayesian optimization libraries of the Python programming language was used. The optimization results are shown in table 1. As can be seen, all three optimizers have reached the point from the intervals where the value of F1 score is maximal. The precision value indicates a quite large proportion of false positive results, while the recall is 100%. All algorithms showed quite good optimization speed. The shortest execution time was demonstrated by dual annealing. In terms of the number of evaluation of the objective function, Bayesian optimization is the most effective. So the use of each of the optimizers provides a significant reduction in execution time and computational costs compared to the grid search. In conclusion, the problem of predicting the success of organ transplantation is critical in the field of medicine. The use of probabilistic neural network is of considerable interest in this context. In this study, we compared the performance of three popular methods for optimizing the parameters of a probabilistic neural network in the case of analyzing a short set of medical data collected by Lviv regional clinical hospital. All three algorithms have demonstrated efficiency, reaching the optimum performance point. The use of optimizers provided a significant savings of time and computer resources compared to a grid search. Thank you for your attention.